Thank you for the invitation, academician.
Gentlemen, excuse me. Александр Михайлович. Александр Михайлович.
Да, я слушаю вас.
Позвольте мне идти спать уже. У меня 4 часа утра, мне в 9 надо на следующее совещание. Можно?
Zinfer Ismagilov, he is in Kemerovo, and now it is 4 o'clock in the morning. Probably we can forgive.
Because it's 9 in the morning. I have another meeting. You know.
Yeah, he's going. He's going to...
I would like to say thank you very much to all participants. And please excuse me.
For the contribution. Thank you.
Okay. See you next time. Bye.
So, Alan, sorry, please.
No problem. Absolutely. And I want to thank Professor Tajima also for the invitation and the great collaboration he's helped us with Eli. And thanks really to everyone, everyone in Russia who is pushing, it's Wednesday now. And I'm mindful of the fact that it's already enough to listen through a lot of Zoom presentations, and to do it at midnight or 4 in the morning is even more challenging. So this invitation is maybe a double-edged sword, but I'll do my best to keep your interest for the next 25 minutes or so and move quickly through some topics. A lot of the science and these developments that we've heard, particularly in the last 3 talks, are very relevant to my talk, but I don't plan to cover those things. So I'm glad that you guys have all covered those bases, especially a lot of the things that Michael, you just presented. I'll give a brief introduction of the extreme light infrastructure. It's a new facility in Europe. We'll take a look at the facilities and I'll give a couple of examples, but really just a couple too, of some research that's relevant, and you'll see exactly the overlap with some of the research that's already been discussed. I won't go into great detail, but I'll give you the references if anyone would prefer to or like to go and dig a little bit deeper. And then what's very important as a trend generally in Europe, I think it's also true in the US, and I know from talking to colleagues in Russia as well, that this is becoming a bigger and bigger consideration. While we're doing a lot of fundamental science, we're doing it at large research infrastructures, oftentimes that happen to not be very sustainable in their operations. We're using lots of energy, and we tend to always, of course, prioritize performance and the science, and oftentimes didn't even give an eye towards or a look towards how to run these facilities in a sustainable way. There's been a trend over the last 10 years or so at the large scale research infrastructures in Europe to think about ways that we can operate the facilities more sustainably as well. So I'll just show a quick case study of what we're doing at Eli to that effect. So Eli is the world's largest, most advanced laser research infrastructure that's particularly intended for users. So there may be more powerful lasers that are used for mission-based purposes, like the NIF laser that's used for fusion, inertial fusion in California and others. But really, Eli is set up as a user facility. It's international. It's the first to be built in Central European states, and it's funded by the European Union's structural funds, which is a specific investment fund used for infrastructure that's been applied in this case for science. These are pan-European facilities, and it was really prompted by technological developments made back in the 80s by Gerard Moreau and Donald Strickland when they were developed a methodology for chirped pulse amplification. This really brought laser technology out of a plateau that it had reached in the early 80s in terms of intensity and the way that we could manage pulses. This, as you'll see, has led to a new generation of petawatt and multi-petawatt class lasers, which opens up whole new areas of research that for those of you who are not familiar with lasers, you may be surprised at some of the capabilities and some of the developments that are moving in this field. So Eli is on the European roadmap. That means it's listed as one of the key research infrastructures in Europe. It's been there since 2006, and we began construction back in 2013. And it's really 3 different facilities, as I'll show you, that have been built. This is following on a trend in Europe generally towards supporting large scale and high power, high intensity laser research facilities. And right now, Europe is really leading the world in terms of the intensity of the number of facilities and the number of petawatt class lasers are really concentrated in Europe. So the ELI timeline is after the idea for ELI, which was actually, written on a napkin back in 2004. So by Girard and a number of other scientists thinking about how to reach an exawatt laser at that time. That's the vision, and that still is a dream that we eventually hope to achieve someday. It set off a kind of a preparatory phase to look at the feasibility of building such a large-scale laser in Europe, and that was funded by the European Union, and it later led to a kind of three-country approach to build the facility. It was understood that it would simply be too much to build as one single facility at one time. There was not an investment concentration. But by using the European structural funds, the Czech Republic, Hungary, and Romania were able to parse out the laser laboratories and figure out a good way to create three complementary laboratories that cover a broad range of laser sources. So that construction has been going on now since 2013, as I said, and has now come into a head. And we're already in the commissioning stage, and we have a number of lasers coming online, trying to get up to our design parameters, and we've already got users coming into the facilities. Again, it's a pan-European project. It's an international facility that's in fact owned by a number of countries, including the two hosts. We have Germany, Italy, Lithuania, which is a real leader in laser science, Bulgaria, and the UK as well. And we expect other countries to join as we now are forming ELI as an international organization. So we're establishing ELI as what's called a European research infrastructure. That's a kind of legal entity that we have in Europe to really allow it to be pan-European and move across country borders. There are some specific advantages to that. Specifically, it means that countries can join. It's not a collaboration of labs, but it's truly countries and ministries that get involved and co-fund the facility. This is the easiest and most convenient legal mechanism in Europe for this, and it was designed specifically for this purpose, and it's governed by a European regulation, which is the highest form of European law that we have under the EC Treaty. The member countries support it. It offers a lot of legal flexibility. As an organization, we have a lot of flexibility in terms of procurement rules, which is quite useful in terms of being able to procure performance-oriented equipment. And we also have some tax advantages as well. Even though it's a European facility, it's also open for non-European facilities to join, or non-European countries to join as well. And we encourage that, and we're talking with a number of countries right now about joining. And you can join as a member or as an observer, or even it's possible to become a strategic partner, in which case there may be some very specific strategic, let's say, scientific reason for establishing a partnership that doesn't necessarily have to do with the country, but it could even be at the institutional level. So it's an open facility, which means that scientific access is very important. It's a user-based facility like a synchrotron or like a neutron facility. So we invite users to submit proposals. It's peer-reviewed, and then depending on the originality, excellence, quality of the proposals, then the users come, and there's no cost to use the facility. The only condition is that it's open publication rule, and eventually the data is also managed by us over the long term, and will be eventually, after a 3 to 5 year embargo period, open to other researchers to integrate into their own research if they like. In addition to that, we also have proprietary access for industry. We encourage industry to think about ways in which they can benefit from the facilities as well. And of course, because they pay for access, then their data is private, and they take it home with them. There's another form of access that's a kind of a new approach in the European Union coming into this new Horizon Europe funding period that goes from 2021 out to 2028. And that's a mission-based approach. And that's very relevant for what we're talking about today. Under the Horizon Europe mission approach, what we really see is an aim towards research that not only leads to innovation, but it's going to have certain effects on a global scale. And we particularly are looking at a couple of mission areas identified by the Commission, including cancer, climate change, healthy oceans, climate neutral cities, and healthy soil and food. So just if you think about the discussion we've had already, you can already start to see the connection to some of these research areas. And this is heavily funded out of a 95 million plus billion, sorry, with a B, budget for Horizon Europe, almost 50 billion is dedicated just to mission-based research. That's very important for our users because oftentimes facilities might be relatively passive and sitting back waiting to get their proposals. What this does is this causes us to lean forward more with our users, think about campaigns and ways that we want to approach these particular thematic areas. So the second pillar will, as I said, incorporate over $50 billion into this. And we're already seeing, for example, with laser-driven particle accelerators, proton therapy applications. We're also talking about and looking into transmutation and handling of nuclear fuel. And we're also looking at new approaches, as you heard earlier, relative to fusion, really leveraging a lot the developments that we see with the high power, high repetition rate lasers that are enabling a new generation of accelerators that are laser plasma driven. So there's three facilities. The three facilities are the Eli beamlines in Prague, Eli Alps in the center there, which is located in Szeged, Hungary, and then Eli MP, which is located in Magarele, Romania, which is near just outside of Bucharest. And each of the facilities has its own particular kind of leaning. So Eli beamlines, as I'll talk about, is more focused on high energy, high field, very intensive pulses. Whereas Eli Alps is focused more on high repetition rates, attosecond, ultra-fast science, and then Eli MP, the MP stands for nuclear photonics. So really pushing the edge of what's possible, not only using laser-driven science, but we also have a gamma accelerator being built there, and we plan to interact those beams together and really explore what's possible when you talk about very high density energy. So right now, in the first phase, we look at transitioning the first two facilities, beamlines and Alps, into this Eli ERIC. Eli MP is still under construction and will join at a later date. And then the idea is to really manage these facilities as a single organization from the point of view of the users and the funding. So some of the science that you see there, obviously the laser development is key for us, but in addition to that, you're also seeing radiation physics, electron acceleration, ion accelerations of different kinds. We're already with lasers reaching GeV levels. So I mean, the Bela accelerator out in California right now has already reached 8 GeV, and you're talking about very compact sources. Now there's a lot of caveats there when you compare with the traditional RF accelerator, but what we definitely see is a trend in the future towards a new generation of particle acceleration. We also see a lot of application in biology and material science as well. We're already working in the UV and the soft X-ray ranges. So plasma physics and high energy density. This is just the kind of meat and potatoes of high energy laser science. This is where we see a lot of very special research being done, also in ultra high intensity interactions, very theoretical physics as well. I'll talk about some more practical aspects today, looking at the facility in Prague, just outside of Prague, and Dolní Břežany is a suburb just outside of Prague. You just get a sense of the proportion for a laser facility. Just the laser hall itself is over 100 meters long, but it's also 4 levels deep into the ground. So we have a combination of the lasers there, and then the other building you see there are support laboratories and offices. And this is the one facility in Prague where you see the lasers at the top level. So 4 major laser sources, L1, L2, L3, and L4. So the L1 and L2 are focusing more on high repetition rate. So you can see with the L1, you're already looking at a kilohertz repetition rate, 20 hertz at the L2. What's very exciting for us, built in collaboration with Lawrence Livermore Laboratory, is the L3 Happels laser. So this is a petawatt class laser operating at 10 hertz. So this is high repetition for this level of intensity. This opens up a whole new field of research. And then of course, we're also still continuing to do experiments in the nanosecond range, 10 petawatt class laser with the L4. And then a range of beamlines as well. Everything from molecular applications, X-ray sources, secondary sources are very important for us, plasma physics, and a number of other things, including acceleration, of course. I think what's interesting to keep in mind when you look at these facilities is the sources are not segmented and parsed and operate independently. The idea is to operate them together and to be able to find different ways to combine the sources together to create new science. Just a quick look at the table, and you can see very quickly the performance where we are today as of November in 2020 relative to the design specification. So we plan to be more or less up to full specification by 2022 with all of the laser systems. Just on average across the board, we've reached about half of the intensity and design specification for most of our lasers. Importantly, L3, just recently, we already see it operating at 400 terawatts at 3 hertz. So we see some very good performance coming out of the lasers, and we're already doing, we're already doing science at the facilities, even though we're going through commissioning now. So one example, which you heard a bit about already, is that's come out of the Eli beamlines in Prague, is really using proton boron experiments, using the lasers to drive that. So the advantages are clear and have already been kind of enumerated there. But what's very specifically nice about this is that it's very clean as a way forward. Where we are in terms of publication, I mean, in addition to a number of publications, you can also see in the bottom right, there's already patents coming out of this technology, and we already are working with commercial partners as well. So this is, fusion, it has gone through many iterations, right? And as we say, tokamaks and ether, still a long way to go. But what I guess the point I want to make is technology is moving forward. And we're seeing steps forward. Laser science is still developing, according to Morse's law. So this is a very fast development that we see. And every time you get, to another level from a terawatt to a petawatt to 10 petawatts, you're going to see very different applications to the physics and the applications. So this is happening now. We're also doing proton boron capture therapy using the lasers. So this is very exciting for us. In particular, working with our partners at the INFN down in Italy. And again, we're not even still at full capacity or full capability yet. Now, let me shift over. I'm mindful of the time, just to kind of look briefly at the different laser sources. This is a good example of the 10 petawatt compressor. You just get a view that it's as big as a locomotive. So these are not your standard tabletop lasers. This is a different class altogether. Now, if I shift to Eli Alps, this is the facility in Szeged, also quite large facility. The experimental hall is a very similar size and capacity as the one in Prague. Both of the facilities are 30,000 square meters each and located on about 5 hectares of land, but with different focuses. So Eli Alps is a bit more spread across the surface area. As I said, we're looking at high repetition rate lasers, but we do also have a petawatt class laser, 2 petawatt, 1 hertz laser being built by Amplitude. And we're also doing a lot of work that requires heavy shielding. So one of the very interesting experiments that I'll talk about in a moment here is taking place with our kind of workhorse laser, the Silos laser, is some experiments relative to transmutation. So I'll point that out a little bit more, and then possibly Toshi will say a few more words later about that in his presentation. Just a quick glance at the facilities. All of this work is taking place in clean rooms. So that's an important point. Keep that in your mind for a moment, because when I come back to the sustainable operations of the facility, that's an important factor. We have more clean room space at our facility than all the rest of the scientific clean rooms in Hungary. So it's a quite large space. We've got more than 4,500 square meters just of ISO 7 and ISO 8 clean rooms. This is a quick table of the lasers, and we're very proud of, and we see a lot of development, particularly around the laser that you see the second and third one there, the Silos laser. This is a very special high repetition rate laser. It's also a single cycle laser. And we're really looking at pulses on the order of less than 6 femtoseconds. So this is very exciting for us, and it's important because it enables some of the science that's coming out. Again, state of the art and built together with Lithuanian partners and some of the companies. Expla, that's one of the leading laser companies in Lithuania. So one of the key research that we see coming out now, we've already also started to do work with transmutation. And of course, I don't need to go into now a long discussion about nuclear waste and what the issues with it are. I mean, I don't even know if this is the most up-to-date or recent, but we see, 270,000 metric tons of nuclear waste around the world. And then also the half-lives of the different materials. It's clearly an issue. And as many positive aspects as there are with nuclear, it's very difficult to say that it's an environmentally friendly technology when we all know very well that getting rid of this and managing this waste is a key issue. And so being able to find ways to kind of mitigate the long half-life, the long kind of radioactive half-life of the materials, and be able to dispose of the material in a much safer way is one of the key elements of, I think, nuclear being able to become, back into the mainstream. And I think we're also very close to that. If we're able to lower the half-lives, then obviously we can think about the number of years that the material has to be stored. Well, that is very important in terms of determining the specifications and requirements of a repository for nuclear waste, and that could considerably reduce the cost of storing the nuclear waste, but it could also, in many ways, make it somehow more acceptable to the broader public. There is already, transmutation, I think, is also one of those areas of science and technology that's had its ups and downs, like fusion, over the years. It's been marginalized at times, but I think it's, again, something that we see coming really into the mainstream. And I think probably one of the reasons for, historic marginalization is just that you have a heavy investment into certain kind of nuclear infrastructure installation, and these kind of approaches opens up new pathways. Just to put it in perspective, in Belgium, they're building a national project. It's not a European project. MIRA is a 1.6 billion euro infrastructure. In the first phase, it's already in process right now, started in 2019, 558 million from the Belgian government to explore this further. And if they're successful in their first phase, then they'll move on to the second phase. And it should be completed with a 600 MeV LINAC and a 100 megawatt reactor by 2036. So a lot of work in this area.
5 more minutes.
Okay, that's going to be challenging. I'll move quickly. Thank you. Just a kind of a quick overview of the transmutation. So this is an idea that came out of Professor Tajima and Gerard Moreau's scheme for a neutron source for laser-based transmutation. So really it's a laser-based neutron source, because in order to be able to achieve the transmutation, we'll have to be able to achieve first a very efficient acceleration with the protons to be able to drive the neutrons. And really it's the development of the high repetition rate lasers that's starting to enable this. So we're doing experiments with the University of Szeged. This is a Hungarian funded project at Eli Alps. And they're looking at the fusion that can be really first the neutron generation. We're developing target systems to be able to understand what the best materials are for that. And then we're looking at the right kind of setup of the laser to be able to do that. So of course, as we're aiming for this mission of transmutation, we're also pushing again the limits of what we can do with the laser. So this is not something that it's not a zero-sum game. We make progress with lasers as we aim towards this higher mission. We've done an experiment last year already with a number of different materials. We were able to generate protons and deuterons with just about everything that we tested from the materials. But what was particularly interesting with carbon was that we were able to very efficiently in the kind of 5 nanometer range targets generate a considerable number of protons, 10 to the 12 steroradians. So it really it proves to us that this is good. We're moving in the right direction. We see signs that we can efficiently generate protons at a useful MEV, and that will lead to neutrons. Just a few words in the last minutes that I have, because this is one of the most the points I really wanted to make. When we're using these large scale facilities, there doesn't really need to be a trade-off between performance and sustainability. Already nearly 11 years ago, a group of European research infrastructures, including CERN, PSI, Eli, the European Spallation Source, started getting together on a bi-yearly basis to have workshops where we look at how to manage the operations of these large-scale facilities more sustainably. In our case, funny enough, it's not really the lasers that are the major issue for us in terms of energy use. Our energy use is being driven by the size of the clean rooms. Now, the reason for that is we're using almost 5 megawatts of power just to cool and keep clean the clean rooms. And we have to expand that to 8 megawatts. So a large portion of our energy usage is really coming from keeping the clean rooms cool and temperature managed. So one of the advantages that we see in this is that, of course, we're in a place where there's a lot of sun, so that makes it difficult to cool. But if 85% of our energy use is just from HVAC in a very sunny area, then what could be a solution to that? And it's a bit counterintuitive. What we've seen from having to clean out and cool these clean rooms is that Szeged actually is in one of the sunniest areas of Central Europe. And really we have a solar isolation potential there for solar, but what we also think is that solar photovoltaic is not really an efficient approach for cooling. It's just simply the energy density for cooling is not there. So what we would like to see is there a way that we could take advantage of the solar radiation to do cooling. And again, I'm not talking about compressor-based air conditioners, but what we're really talking about is thermal-based cooling. And when you look across the world and you see where energy is being used, and while it's true we tend to focus on things like transport, et cetera, what we see really is more than half of all the energy being used in the world is used for heating and cooling. And that trend is probably not going to go down. So we thought, well, we need to really take a closer look at what this means for our facility, as most of the energy demand that we also see is related to cooling. And so what we've decided to do is look at a solar cooling system that's thermal based. So it's an absorption based cooling system that relies on the sun in the summer to be able to help us cool the facility, and particularly to cool the clean rooms. And what we see is it has a much higher cost of performance, or coefficient of performance, than the compression chiller based system that we had originally installed. We believe that we can reduce the energy consumption on the cooling system by up to 80%. And we're able to also have a much more reliable operation in the sense that these absorption-based chillers tend to be much more long-term in terms of they don't wear out as fast as compression-based systems. So basically, these are lithium bromide systems, which is a very important desiccant, and we use just thermal collectors to be able to collect the heat up to 88 degrees. And then based on that, our chillers can use that to cool it down to as much as 7 degrees Celsius. And that, what this does is it not only takes away the heat, but it also takes away a good bit of the humidity, which is important for us. So without going into the different kind of collector types, what I just want to say is this allows us to use very straightforward, basic thermal heat collectors. These are not fancy state-of-the-art photovoltaic collectors. These are really just off-the-shelf, large-scale industrial collectors. We have a capacity for almost 20,000 square meters of collection at Eli, so that's an advantage based, relative to our site. And we think that we have the capacity for up to 14 megawatts of thermal capacity from this system. Okay, so maybe just to kind of close out, the important thing for us when we look at the operations, this does one other critical thing. It actually freezes our energy cost around the cooling, because one of the things we as a public facility have to worry about are the rise in energy cost over the next, let's say, 10 to 15 years. What we see is not only will we get a payback in less than 15 years, but we also see that we'll be able to freeze those costs. So that payback is based on a 2020 euro value. And as we see the euro change and as we see energy costs go up, we expect that this will give us not only a saving, but more importantly, it'll give us stability in terms of energy cost. So the last part about that is, in addition to that, around the Eli facility, there will be a large industrial scientific park built. And so this system, while we'll pilot it at Eli Alps, it should also apply for a much larger kind of area that will encompass several hectares and probably 20 to 30 different scientific labs and research-oriented companies. So that's the advantages of the solar thermal. We're very happy with this approach, and we're talking with other labs that also use energy recovery techniques from their machines and are thinking about integrating this into their facilities. So we think that there's a significant trend at the large RIs in Europe towards sustainability, also in the research as a criteria for scientific evaluation, as I pointed out. But I think there's also a growing insistence among stakeholders and even our users that we need to be more sustainable and we need to rethink our operations. And so a number of large-scale facilities, including Eli, are doing that at this time. So I think that's it. Thank you very much. And I appreciate the extra minute or so, Professor. Thank you.
Thank you.